Assalamualaikum and hi everyone. We are from group section 3. Our topic is collapsible soil. First of all, we must know the definition of collapsible soil. Collapsible soil is unsaturated soil that undergoes a rearrangement of particles and reduction in volume upon wetting, additional loading, or both. The characteristic of collapsible soil is low natural moisture content, high void ratio or low density, and unsaturated. Next, this is schematic diagram of collapsible soil. From the left side, it is collapsible soil structure before wetting. At high void ratio, that means the soil particles are loosely packed with many air gaps, which is void in between. At weak cemented bonds, that means the soil grains are held together by fragile connection like clay films, salt crystal, or other temporary cements. These bonds are stable in dry condition but dissolve or weaken when water is introduced. For the right side, it is the effect of water on the soil. Downward arrow means wetting. When water infiltrates the soil, it weakens or dissolves the cemented bonds. And for the horizontal arrow, it means collapse or settlement. As the bonds break and the void lose support, the soil particles rearrange into a denser state. This can damage building or roads resting on the soil.
Details of geotechnical structure associated with collapsible soil. First, we have foundation. We can use shallow foundations such as pad or straight footings because they are highly vulnerable to differential settlement. And we also can use deep foundations such as piles because they are often used to transfer loads past collapsible layers. So the second one, we have roads and pavements. Flexible pavements can crack and deform due to uneven settlements. This layer may require stabilization. So for geotechnical problems during construction, the first one is unexpected settlements. Buildings or roads experience uneven or sudden sinking after rainfall or irrigation. So for the second one is cracking in structural elements due to soil instability. Changes in soil moisture content can cause significant foundation movement and subsequent cracking. And certain soil types like expensive clay are more prone to volume changes and contribute to cracking. And for the third one is infrastructure failure. Collapse of underground utilities and pavements due to compromised soil strength. So for proper solution, the first one we have collapse and wetting. So we can use pre-wetting and compaction of soil to induce and control collapse before construction. And the second one we have weak bearing capacity. We can replace with engineered fill or granular backfill. And the last one we have foundation instability. We can use deep foundations such as piles or piers.
Laboratory testing or collapsible soil laboratory test is a soil sample that has the potential to compress or collapse when it is saturated with water, and it is particularly crucial for loose, unsaturated soils like silty sands. If this behavior is not appropriately handled in the design, it may result in structural damage. Two common laboratory techniques that are conventional is odometer and the triaxial techniques. Both take into account important factors that govern the densification of the majority of soils after soaking, including the dry density, the initial water content, and the applied load. For odometer test, there are two types, which is single and double. For single odometer collapse test, the undisturbed soil specimen that in its natural moisture content loaded to a stress level between 200 to 400 kilopascal in the conventional odometer, and then it will be submerged in distilled water that will cause collapsion. This idea is to predict the amount of distilled water that occur deformation of soil when the surface is wet. The graph shows the results of single odometer test where the unsaturated soil or dry specimen phase collapse strand became saturated specimen. The second one is double odometer collapse test where there are two identical samples that are placed in the odometer. The first sample test evaluated at in situ moisture content while the other one to be fully saturated and loaded identically. The amount of deformation occur would happen at any stress level where the soil becomes saturated. That shows the difference between the compression curve. The graph shows the result of double odometer test. Critical stress can also be called the highest stress level, which shows where the stress level where the loose structure of the dry sample degrades and the two curves converge beyond it. The second laboratory test is triaxial test. This test reproduces the in situ stresses that exist on the sample original location. The figure shows a cylindrical core specimen that can be rock, soil, or granular material that is subjected to triaxial test in order to assess its mechanical properties and shear strength. The specimen then sheared to failure to obtain its shear strength characteristic. Usually, the specimen will be saturated first, then consolidated, and ultimately sheared under compressive circumstance. For triaxial test, there are three types. Unconsolidated undrained, or UU, is a quick test. Meanwhile, the second one is consolidated undrained CU. It is a little bit long than the first one. The third one is consolidated drained CD. It has a long duration test. For the UU, this method uses the total stress to measure the shear strength. The specimen compressive strength depends on the amount of geostatic stress in the fluid, as it cannot be consolidated and must retain its original water content and structure. 3 specimens taken, same sample, is from the same sample, and exposed to various confining fluid pressure in the axial chamber. Shear strength, in other words, undrained shear strength, will be constant across tests as long as the soil is completely saturated. The second one is ECU. This method uses the effective stress to measure the shear strength. Specimen in saturated condition that allow to consolidated, or consolidated is a process that alters the structure and water content of soil at the confining fluid pressure in the axial chamber. After consolidation, the specimen is put through a control load application process that prevents drainage to quantify the pore pressure in that soil. The last one is consolidated drained CD. It has a long duration test, just like I mentioned before. This method uses effective stress to measure the shear strength, just like before. The specimen is saturated and slowly consolidated in order to prevent excessive pressure from being built up in the pores by the shearing at the confining fluid pressure in the axial chamber, just like before. After the specimen go through consolidation, a regular weight is applied to the specimen, allowing moisture to escape without risk of pore pressure accumulation.
Okay, now I'm going to explain the concept of collapse potential, a critical factor in geotechnical engineering, especially when dealing with unsaturated soil. So, collapse potential is defined as the measure of a soil tendency to undergo sudden reduction in volume upon wetting under constant total stress. And this typically occurs in loose, low-density soils like silty sands, where the soil structure becomes unstable when moisture is introduced. Okay, then I will explain the equation above. So, collapse potential, abbreviated as CP, is calculated using this formula, where E equal to E initial minus E final. E initial is the initial void ratio. That is the void ratio of the soil before wetting. E final is the final void ratio after the soil has been wet. And CP is expressed as a percentage. That's why we need to time by 100. So, I will explain the concept here. This equation helps us understand how much a soil sample collapses when it gets wet. In simple terms, it compares how much the soil compressed after wetting to its original volume. Void ratio, as you may know, is the volume of a void over the volume of solids. So, a decrease in the void ratio due to wetting indicates that the soil structure is collapsing. Okay, now I will explain the table, which is the collapse classification table. Based on the calculated CP value, we can classify the severity of the collapse. This table shows how it works. So, if CP that we get is under 1%, so there is no problem at all. But if it is 1 to 5%, we have moderate trouble. If 5 to 10%, this is classified as trouble. Then, if it is 10 to 20%, means severe trouble. And if the CP is above 20%, this indicates very severe trouble. So, in summary, this simple yet powerful equation gives us an insight into the potential risk of soil collapse due to water infiltration. Understanding collapse potential can help prevent structural damage and ensure safer construction.